Okay, let's start. Today, this is the live session for the week 6 assignments, in which we will discuss the questions related to the numerical response of the structure, say central difference method or Newmark's beta gamma method, and the another part is the response spectrum analysis of a single degree freedom of the system. So we will discuss here number of question 6. So let us discuss today's start the today's session. So in which the first question is the what is the value of beta and gamma for a Newmark's beta method for constant average acceleration and the linear acceleration method. So I am giving you the for the constant acceleration table four options, and for the linear average acceleration four options. So can you tell me what is the value of the beta and gamma for the constant average acceleration and for the linear average acceleration? These two questions are there. So constant average acceleration means like for calculating the response, we are considering the response is constant average, and for the linear acceleration means we are considering our acceleration like varying this. Okay, so we will get these 2 points here, and considering this constant and average and the linear, we will calculate u dot I and ui plus 1 in both the methods. And if we will look up at, like for the constant average acceleration, the answer for this beta is 1 by 4 and the gamma is 1 by 2, and for the linear acceleration beta is 1 by 6 and gamma is 1 by 2. Okay, now these are the answers. Like for the constant average acceleration, the answer is A, and for the linear acceleration, answer is C. Okay, now let us move to the another question, which is the question related to the central difference method. Like we have given the mass, we have given the stiffness, time period of the system, and the also the like the natural frequency of the system. Damping in the system is given as a 5%. So we have to determine the response corresponding to a cycle. Half sine pulse is given to you, so we have to determine the response at the step of 0.1 second. So here we will calculate the response up to 10 second. So for the uh, central difference method, we have some procedure for the central difference method. Like for this, first we do the initial calculation. The initial calculation contains u double dot or the initial acceleration. This is the kind of the limit, you can say, like the initial acceleration is calculated as a p naught minus cu dot naught minus ku naught by m, and this is the displacement previous like the for the previous step, that is the u naught minus delta t u dot naught plus del t square by 2 u double dot naught. So here delta t is your time step, u dot naught is your initial velocity, and this is your initial acceleration. Now the changed stiffness is m divided by delta t square plus c divided by 2 into delta t, and these are the coefficients a and b, which is m over delta t square minus c over 2 into delta t, and b is given to you k minus 2m over delta t square. And after that calculation, for the ith step, we calculate the force in the next step, which is calculated by the P initial P force in the ith step minus A into Ui minus B into Ui, which is displacement. So the displacement for the next step can be calculated as Ui plus 1 is equal to P updated or the new load divided by the K. Okay, so in this situation, first we consider the initial condition. We consider like the u naught is equal to 0 and u dot naught is equal to 0. That means the my system is at rest. So for this, first we calculate what is our damping coefficient c. C, you know what is your c? C 2 xi m omega n. So damping ratio is given to you 5%. Okay, and mass is given to you 4500 45,594, and the omega is also given to you in the question, that is 6.283. So your damping coefficient is comes out to be 28,584.89 Newton second per meter. Now we calculate the initial steps, like as we discussed earlier. Like these steps, how we find out these steps? These all the explanation has been given in the like the week 6 content of the NPTEL. If you go through the lecture, like the module 1 of the week 6, you will find how we get these values. So here I will discuss the example of this related to this. Okay, so first, like I have given initial conditions are 0, u dot 0 is 0, and the u dot 0 is 0, like initial displacement, and initial velocity is 0, and the initial force, like what is my the force vector, it is something like this. So t is equal to 0, my force is also 0, so my initial acceleration become as 0. Now I have to calculate u minus 1, so that is also 0, because u dot is equal to 0 is given to you, and this u dot naught, u double dot naught is from here, and u naught is also 0 as given in the system. Now come to the stiffness of the system, that can be calculated by m over del t square plus c over 2 delta t is equal to m over del t square. So m is given to you 45,594 divided by zero point 0.1 square plus c damping coefficient we have calculated here. So that we put the value of the damping coefficient, and time step is zero point 0.1. If you calculate it, that comes out to be 47 kilonewton per centimeter. Okay, so Diksha Thakur, here we are discussing the central difference method. If you have any doubt during this, you can ask me. Okay,
Sir.
am I audible?
Yes, sir.
Okay, so I am discussing like in the last PPT, last slide, I have discussed these formulation. Now I will provide you the like the formulation and all the coefficients. The next part in which you will be able to calculate your response. Okay, so the stiffness you can calculate like this. Now the coefficient k is calculated. Now a coefficient is given by m over delta t square minus c over 2 delta t. If you put the value of m and c and the time step value, you will get the a coefficient as a 44.16. Same way you can find out your coefficient b, which is k minus 2m over del t square, which you will be find out minus 73.18. Okay, now calculation for the ith step. So for the ith step, if like the updated p is given as pi minus a ui minus 1 minus b ui. So I will put the value of a and the value of b. So when you put the value of a and b, my equation is pi minus 44.16 ui minus 1 plus 73.18 ui kilonewton. Same for the my response in the I plus 1 step, which is P divided by K cap. So that will comes out to Pi cap divided by the 47.03 centimeter. So now, like, after calculating these steps, like the formulation you can find out from the NPTEL modules, and like after getting these two, like these two things are important, like Pi cap and the UI plus 1 step, and we have to calculate the response corresponding to different time step, says 0, 0 0.1, 0 0.2, 0 0.3. So for this, I have created a table. I am providing the formulation also. So can you tell me, like, the force is given to you the half sine pulse, something like this. So at 0, time is equal to 0, force is 0. At time is equal to zero point 0.1, the force is 25 kilonewton. At time is equal to zero point 0.2, it is something 43.3, so on. So I will provide this value pi. So after given to you pi, you can calculate over your ui minus 1. What is your ui minus 1? That was the 0 initial. And what is your ui initial? Ui for the 0th step, u naught, which is given to you, which is also 0. So if you have these two value, what is your pi cap? Can you tell me? Like in this equation, put these all these three coefficient. Can you calculate your pi cap? Updated p value. Anyone? Like as pi, like for the zeroth step, p0 is 0, ui minus 1 says will become as a u minus 1, which is 0, and u0 is 0. If I put these value in this equation, I will get pi cap as a 0. If my pi cap is 0, then my ui plus 1, after getting this I will put this here. So my ui plus 1 comes out to this, which is says for the zeroth step that will be that will become u1. So my u1 become this 0. Now for the first step, says I is equal to 1. For the I is equal to 1, my p1 from the half sine pulse, from the half sine pulse, as I said, at delta t is equal to zero point 0.1, my pi is equal to 25. Now for the ith step, says for the u1, that term become u0. For here I will find u0. What will be my u0? Like for the first step, and that will be the u1. What is my u1? So what is my u0? So this is the u0 here. So that term comes to here, and that u1 term come to here. If I put this, so that will become 0, and for the u1 also that becomes 0. If I put these value in this updated pi cap, I will find my pi cap as a 25. Now if I will put the pi cap in this equation, I will find out ui plus 1, that is comes out to be 0.5316 centimeter. So this is my u2. Any doubt up to this point? Anyone? Let's say any doubt? Do you have any doubt? Anyone? If not, then let us discuss the another step. For the delta t is equal to zero point 0.2, my force is given to you 43.3 second. For now this time for second step, my this ui minus become as a u1, and this is become u2. So for this becoming u1, what is my u1? That is 0. You can take it. What is my u2? That is comes to here. So u1 is 0 and u2 is 0.5316. And if you will find out what is your pi cap, now put the pi is equal to 43.3, ui minus 1, or the u1 is 0 and the u2 is 0.536. So if you will put these values in this equation, I get the value of pi cap, which comes out to be 82.20 kilonewton. And now after putting this, getting this value, I will put this here, and I will get this again here. So that is my u3. Okay. Now next, at time step t is equal to zero point 0.3, my load is 50 kilonewton. If I will put like this is become as a u2 now for third step, and this is u3. So what is my u2? My u2 will become this 0.536, and what is my u3? That will become this, says 1.74. And if I take like find out the pi cap, my load is become as a 154.466. And if I calculate again by putting this into this equation, I will find out ui plus 1, or says u4, comes out to be this. Okay. Now the same step for the fourth step, same procedure. Fifth step, sixth step, like these are the steps I have calculated. Like up to this the loading is given us, then zero loading. Like this is the half sine pulse, the time duration is given to you zero point 0.6, and then it is 0. So I got the response. And same for these time steps, I can get the theoretical response. Do you know what is theoretical response for the sine pulse? For the sine pulse, that is p naught by k into 1 minus omega by omega n square into sine omega sine omega t minus omega by omega n into sine omega n t minus TD. So that is the response for the full sine pulse. So for the half sine pulse, you will divide it like the frequency will become as a omega by 2. So these are the theoretical response you can calculate. And if you you can compare like your what is your solution around like a time step 0, like 10th step, that is coming around 3 approximately at the point 0.5 time step, that is coming around this way. So this way you can calculate your response for the ith plus 1 step. Is there any doubt in this question? Anyone? Can you hear me? Am I audible to all of you? Okay, let us discuss another question. If no one is here, if you can hear me, can you write in the chat box like yes or no? And if you have any doubt, you can also in the write in the chat box. Okay, so now we are moving to another question, which is related to the response of a single degree of freedom system. Like they're finding out the response due to the response spectra of a system. Like a small story, one story reinforced building is given to you, in which that there are two column, one is shorter and another is the longer. This is 3 meter and the longer one is the 6 meter. The total dead load supported by the beam level is the 5000 kg, says here. The 5000 kg load is given here, and the e section is given to you 25 by 25 centimeter, and the column is hinged at the bottom, and the E young modulus is given to you 20,000 MPa, and we have to determine the response. If the design spectrum is given to you this, and it is scaled to 0.25 G, mean whatever response will I will get through this response, I have to multiply it with the 0.25. Okay, and what are the response quantities are displacement at the top of the frame, and the bending moment in the long column and bending moment in the short column. Have you understood the question, everyone? Vasudev? Vasudev, am I audible?
Yes, yes, sir. Yes, sir.
Okay. Then,
Yes,
have you understood the question?
yes, sir.
Okay, so let's start the solution for this. Like, first, I have to find out what is my I value, moment of inertia of the columns. So, what is my moment of inertia for a rectangular section? BD square by 12. So, can you find out the moment of inertia?
Just a minute, sir.
Next, the size is given to you 25 by 25. So, that will become D4 by t की power 4 divided by the 4 or 12. Simple. So if you calculate the moment of inertia, it comes out to be 32,552.083 centimeter to power 4. Now we have to determine the stiffness of the frame. Can you determine the stiffness of the frame? Like for the if my one end is hinge, what is the stiffness of the system? Like says two type of things are here. Like my one end is fixed, like says like the rigidly connected to the beam, and it is one is fixed from the bottom, and another frame, same frame, which is hinge. So for a hinge, can you tell me what is the stiffness for the single column? K.
Is it 3a by L cube?
Yes, that is the 3I by L cube, and for the fixed, that will be the 12I by L.
12a by L cube. Yes, sir.
So now you can you calculate the stiffness of the system? Like E is given to you 20,000 MPa, and the frame is given to you like this. Like the one side is 3 meter, another side is a 6 meter. You have I value also, so you can calculate the stiffness of the frame.
For one column, it is 2.411 into 10 to the power 6.
You have to determine it's the sum, like the total stiffness of the frame. Like you have to sum up this both the
Yeah.
stiffness.
Sir, is it 3.31 into 10 to the power 6?
Let me check. It is coming out to be 8. It is come out 813,802.075 Newton per meter.
Yeah.
Is it correct? Whatever you are getting, or is there any like in the disparity in the answer?
So, sir, instead of 20,000, I have taken it as to be 200 into 10 to the power 9. So
L-
that is why my answer is different.
Oh, that is a
Yeah.
20,000 MPa. Okay.
I've
So
taken it first thing.
after getting the stiffness, the mass is given to you 5,000. So can you calculate the what is my time period of the frame? Like you have the stiffness, you have the mass, you can calculate the time period simply 2 pi square root of m by k.
So it is 12.75.
How much that can be the time period? 12.5 can you?
12.7. Okay, that is omega, natural
Okay,
frequency.
yes, yes. Because time period
Yeah.
can't be that much high.
Yeah, it is 0.492 something.
Yes, that is 4.4924. That is my time period, and the natural frequencies comes out to be 20.575.
12.75. Yes.
Okay, now from the response spectra, at t is equal to 0.492 second, I have to find out what will be my response. So the response spectra, like I will show you the response spectra. At t is equal to 0.497, can you find out what is the value? Are you able to read it the value from the response spectra? Are you able to see it, the response spectra?
Sir, will it be constant 2.71?
Yes, that will be the SA by G. So after getting the SA by G, in the question we have told that your response will be scaled to 0.5 G. Okay, so whatever the response we have get SA by G, we have to multiply it with the zero point 0.5. No, not 0.25, 0.5, that will be equal to 0.25. So we scale it to multiply it with the 0.25 and then multiply with the 9.81. So our response, like the spectral acceleration, is comes out to be 6.46 meter per second square. So part A, can you
So I
calculate?
have not, sir, I have not understood why it is multiplied with 0.25.
That is given to you in the question.
Okay, 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 sir.
That whenever you in the read in the question, that is
Yeah, yeah.
described that you have to scale it up to this level 0.25 or zero point 0.5 or 0.68, whatever the
Okay,
it is required. So now
okay,
for
sir.
the part A, like we have to find out the what is the peak displacement. So can you find out the displacement if you have the spectral acceleration? How to find the peak displacement?
So that A divided by omega n square.
Yes, that A divided by the omega n square. So that is comes out to be around 40.88 mm. That is our peak displacement. Now the another question,
Yes, sir.
part B and part C is contained, like what is the bending moment in the shorter or the longer column. So for the part B, and this is also part C also same. So if the column is hinged at the base, what is your bending moment? Like if
So
your
that will be K into this displacement divided by
yes, like if your
multiplied by distance.
yes, if that is your settle by some sort of delta,
Yeah.
so that will be your 3I by L square into delta. So that is our bending moment. So you can calculate the bending moment simply for both the, like you have the displacement at the top, deflection in the both the columns, that is 40.8 at 88 mm. So you can calculate the simply bending moment. You have the length, you have the E value, you have the I value. So if the bending moment in the short column, it comes out to be 88.7 kilonewton meter, and for the longer column, it is coming out to be 22.17 kilometer. Okay, is there any doubt in this question? Any doubt? Have you understood?
Yes, sir.
Okay. So now I am moving to the another question, which is related to some derivation type question. Like we have to derive the equation for the deformation, for the velocity, for the acceleration, response spectra. Like the response spectra for the deformation as well as the velocity as well as the acceleration. For a ground acceleration is given to you ug double dot t is equal to ug naught dot into delta t, or where delta t is the direct delta function and u dot g naught is the increment in the velocity or the magnitude of the acceleration impulse. So we have to plot the response spectra for the deformation, for the velocity, and for the acceleration. A damping ratio if is xi is equal to 0 and xi is equal to 10%. Okay. So have you understood the question?
Yes, sir.
Okay. So if I have a equation of the unit impulse, mu double dot plus cu dot plus ku is equal to pt, where pt is my delta t. So what will be my solution for the damped equation? The solution of the unit impulse is given by the ut is equal to 1 over m omega d e raised to power minus xi omega n t minus tau into sine omega dt. Is there any doubt in this equation? Because that is discussed in the week 5 as well. Is it okay up to this equation?
Yes, sir.
Okay, like if this is the solution for the unit impulse. Now if you have an equation of motion like this, mu double dot plus cu dot plus ku is equal to pt, and where pt is given to you minus m ug double dot, and where ug double dot is given to you as ug ground dot into delta t. This, so that, like my equation will become pt become as a minus m into ug naught delta t. So only the difference is that I have to multiply this with the my solution of the unit impulse. Okay. So my equation is become this: mu double dot cu dot plus ku is equal to minus m ug double dot. And if I will put the value of the ug double dot, that becomes as a minus m ug naught dot delta t. And this is the only the multiplication. Like if I will multiply this with the m ug naught, then I will get the solution of the equation. So this is the solution of this equation. For the, if my ground motion like the expression is this, then the solution is becomes this: minus ug naught dot divided by the omega d into exponential minus xi omega and t minus tau into sine omega dt. Is there any doubt up to this? Any doubt?
No, sir. No, sir.
Okay, so if you have this equation, now we have to find out, like if we have the ut, we can find out what our like the velocity. For the velocity we will multiply with this the omega n for the velocity, and for the acceleration we will multiply this the omega n square. For the maximum response, u dot t is equal to 0. First we have to find out whatever the maximum response. So we will determine like the whatever the ut we have to differentiate it, so that we can find out the maximum response. If we differentiate it, we will get this equation and equate it to 0. And then if we rearrange the terms, we will get the like exponential terms can't be 0, so that terms only remains here. This one minus sin omega and sin omega dt, omega d cos omega dt. And if you will again rearrange the terms, then you will get the tan omega dt is equal to omega d divided by the xi omega n. So omega d, what is your omega d? That is omega n into 1 minus xi square. Omega n into 1 minus, or this omega n cancel out with this. So my t is become as a 1 by omega d into tan inverse 1 minus xi square divided by. This is the t value, my response would be the maximum. So now by the trigonometry, if my this is the triangle and the my angle is says omega dt, and this is my perpendicular 1 minus xi square, and this is the, so what will be this? This will be xi square plus 1 minus xi square, that will cancel out, so this will remain 1. So what will be my sin omega dt? Sin omega dt is become as 1 minus xi square divided by 1, so that will become this. Simple. Okay, now we have to put this value in the equation 1, whatever we get the value of the ut. So my ut was in the ut I have put the value of, this is the value of the t, and where the sin omega dt is multiplied, I have put this equation 1 minus xi square. And if I rearrange the terms, like if I will rearrange the term, that terms will cancel out this inside, and this omega d will cancel out this. So after rearranging the terms, I get the u naught as a u dot g naught divided by omega n into exponential minus xi 1 minus xi square into tan inverse 1 minus xi square by xi. So now this is my the maximum response. So for the response spectra, what is my d? Whatever the u naught is, my d is the same. For the response spectra at different time period, I can calculate omega and I can write it as a omega n is equal to 2 pi by tn. So tn goes to up in the numerator and the 2 pi in the denominator. And then after getting the d, I can get the v is the 2 pi divided by the d, this is the omega n. And what is my acceleration? That is the omega n square. So for damping is equal to 0, if I will put the xi is equal to 0 in this equation, if I will put the damping is equal to 0, so this whole term becomes 0, and exponential 0 is, what is the exponential 0? Is 1. Okay, so if you put this value, so my d become this. all outside terms are 0. And if I multiply it with the omega n, so my velocity, pseudo velocity is this ug naught, and my acceleration is this 2 pi by tn into ug naught. And for the damping point 1, if I will put the damping is equal to point 1, then find out the coefficient value, like the inside the exponential terms, that is the coefficient 0.86 into 26, and this is the velocity, and this is the 2 pi by t into tn, like whatever the omega n. This is become by the velocity. If I will multiply this with the omega n, like multiply this with the omega n, give you the velocity. Multiply this with the omega n square, this will give you the acceleration. So now we have to plot for the velocity, for the response, for all, for both the things. For the damping is equal to 0 and damping ratio is equal to zero point 0.1. So for the deformation response, for the damping, like the dashed line shows for the damping is 0, and for the solid line it shows for the damping is equal to zero point 0.1. Okay, like this is a something directly slope, like d is directly depend on the tn. Okay, like the d over ug naught is taken out, like the in the denominator, so that is become as a 1 over 2 pi into tn. Now same for the velocity response, this will be the constant v is equal to, if I take this is as in the numerator, so this is a constant, and for the damping is equal to zero point 0.1, that is the 0.86, that will be multiplied with the 1. Now for the acceleration, this is the response for the solid line, like the for the damping is equal to 0, this is a dashed line, and for the damping is equal to 0.1%, this is the solid curve. So this is the, these are the response. Okay, any doubt in this question, anyone?
No, sir.
Okay, if not,
It is understood.
okay, now let us discuss the another question. Now these are the simple questions, like if a single degree of system supporting a weight is equal to 25 kilonewton and has a natural time period of 1.59 second, given the peak is equal to 127 mm, determine the pseudo velocity and the peak value of the equivalent static force. So can you determine the the velocity? Like the deformation is given to you. Can you determine the velocity? Like the supporting weight is given to you 25 kilonewton, time period is 1.59. So for the calculation of the velocity, pseudo velocity, I want this deformation should be divided by the omega n. So for this, first I have to calculate the omega n. So what will be the my omega n? That will be the, first I have calculated the supporting mass, and is equal to w omega w divided by the g. So this is the weight, 25 into 1000 Newton, and that is the 9.81. So that is in the kilogram. And the natural frequency can be calculated as 2 pi by Tn, so it comes out to be 3.95. So I can directly calculate the solar velocity by this equation. V is equal to d by omega n. Sorry, that will be the multiply, not the divide. So if you calculate the velocity, it comes out to 0.501 meter per second. And now if you have given the like the, you have the frequency, you have the stiffness, you have the displacement, what is the equivalent static force? Can you tell me directly? Can you hear me? Okay. So like you can determine the equivalent static force as a F equal to kx. So equivalent static force can be found out equal to F equal to kx or F equal to k into u naught. So can you determine the stiffness? Like you have the time period, you have the natural frequency, you can directly calculate the stiffness. So for calculation of the stiffness, k is equal to m onto omega n square, and is given to you 2548.42 kilogram, and the natural frequency is given to 3.95 square. Okay, and then if you will multiply this, you will get the stiffness in the kilometer area, 39.76 kilometer per meter, and you can find out the force directly as F naught is equal to ku naught. That comes out to be 39.76 multiplied with the displacement. What is the displacement? That is given to you 0.127 meter or the 127 mm. So I am multiplying this with the I got the equivalent of static force is the 5.05 kilometer. Okay. So this is a simple question. So now we are moving to a longer problem. Is there any doubt, Basudev?
No, sir. No doubt. Understood, sir.
Okay. So now we are moving to another and the longer problem. Says a full water tank is separated on a 25-meter high cantilever tower, and it is idealized as a single degree of freedom system with a mass as a 50,000 kilogram. And the lateral stiffness is given to you 700 kilonewton per meter, and the damping ratio is given to you 5%. The tower is supporting the tank is to be designed for a ground motion. Thus, the ground motion design spectrum of the ground motion is given to you here. This one is the design spectrum. So, and this design spectrum is scaled to 0.5 G. So, determine the design value of the lateral deformation. In the first part, we have to determine the lateral force and the base shear. So, you have given the mass, you have given the stiffness. If you can calculate the direct time period, and from the time period, you can calculate the SA by G from this graph, and you can calculate the your displacement as well as the base year. In the part B, like the designer is feel like the deformation is like higher, like in the system. So for reducing the deformation, he stiffen the tower, like increase the stiffness. So now in the second case, he increase the stiffness to the like it divide the designer to 2 times. Like it now it's become the 1400 kilonewton, and then assuming the same data, we have to find out again the same thing. What is your lateral deformation and what is your base shear? Now after that, stiffen the tower. Now again, like the designer is thinking like if I again increase the mass, what will be your like the displacement and the base here. So we have to compare these cases, like all three cases. Okay, now let me go one by one cases. So in the first case, part A, you have given the mass is a 50,000 kg, damping is 700 kilonewton meter, damping is 5%. Can you tell me what is your time period? So if I calculate the time period with the mass and the stiffness, it comes out to 1.69. So in 1.68. So from the response spectrum, let's say first we find out the natural frequency omega n, that comes out to be 2 pi by T n is 3.7. So from the response spectra, it time is equal to 1.679. So from this response spectra, can you tell me what is the value of the SA by G? At 1.69 from the graph. Like my time period is fall in
Sir,
this.
is it like this? From the 2.71 value, from 0.66 onwards, we have to deduct the value of 1.8 into t to the power minus 1.
Yes. So at the like the time period 1.69 over SA by G value is the 1.8 into Tn raised to power minus 1. Okay.
Okay.
So this is SA by G is given to you as a 1.8 divided by the Tn. So what is your Tn? It is 1.679 and we get the 1.07. Now in the
Sir,
question, yes, yes,
can I ask question?
yes, yes.
Sir, it is like 2.71. Then just a minute, sir. 2.71. Then what we have is 1.679 minus 0.66
No,
into
no, 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 no.
1.8 into 1.42.
No, this is not the like you don't need to do the iteration or something like that.
will you please explain how to get it from 2.71 to the value of 1.679? Will you please explain that?
No, like this is like from this graph now. You are asking like how to extract this value.
Yes, sir. Yes, sir.
Like in this graph, I have given this graph. Forget about these lines first. Okay. So I have this graph like up to the value of like if my time period is 1 divided by the 33 second. So my value will be remain 1 SA by G. If my value is increasing from 1 by 33 to 1 by 8, say 0.25 or 0.15, whatever that is, that my value is the 11.7 into Tn raised to power 0.704. If my time period is in the range between this range from 1 by 8
Yeah,
to
that is constant. That
that
is
is constant.
constant.
If my time period is in the range of this 0.662 to a 0.412, my value directly is given by this SA by G is equal to 1.8 divided by the Tn. Simple. Like what is your question here?
Sir, just a minute. Sir, just I wish to, I want to ask a question like, is it calculation like 2.71 minus bracket 1.679 minus 0.66
No, no,
into
no, no. Like
1.679 inverse?
no, you don't need to do that like that. You have to take only this value, like take in the directly value. Like like in this, like you have like whatever the value of if your time period is between this range, these two lines, then your SAYG value directly given as a 1.8 divided by Tn. This is your value.
Okay, directly we can use
Yes, yes.
that value itself.
Yeah, you don't need to do like the like if you are 2.71 and then you need to like if that is like that is a slope if you have given or you have like that's what that was the missing, like says you have given only that line and you don't have the value of 1.8 divided by Tn, then you may need to like this is your 2.7, this is your something point, you can go and then you need to iterate it, but here the slope value is given to you. Okay.
Okay, so just it will be 1.8 into whatever value we have 2.7, sorry, 1.679
Inverse. Yes.
into raised to power minus 1.
Yes. Yes. That is the simple.
That's all.
Yeah.
Okay, okay, let me check sir calculation. Okay, sir.
Okay. So that will be your value directly. So now we have given in the question that design spectrum is scaled to 0.5 G. So now I need to multiply it with the zero point 0.5. Okay. So my SA by G become as a 0.536. Now if I have SA by G, I can calculate what is my SA or the spectral acceleration is 0.536 multiplied with the G. So that comes out to be 5.258 meter per second square. So now I have the spectral acceleration. I can find out what is the lateral deformation. That is the d is equal to a divided by the omega n square. So that become as a d displacement is coming out to be 375.5353 mm is my lateral deformation of the tower. Now the base shear directly can be calculated as F is equal to kd. So the stiffness of the system is given to you 7,000 kilonewton per meter. So if you multiply it with the displacement, like the directly base here, you can find out 262.85 kilometer. Okay. Now in the part B, if the stiffness is doubled, says 1400 kilonewton per meter, and the damping ratio is the same, so your time period is become as a, if you calculate the time period, it reduce because your system is stiffen. So if your system is stiffer, then the time period is lesser. So that is reduced to from 1.62 it will become 1.18. Okay, so after that if you calculate the natural frequency omega n, it will become as a 5.29. So from that 1.1874, the response spectra is same, like that is also lies in this range also, 1.8 divided by Tn. So your SA by G is become as a 1.516. Now the design spectrum is scaled to zero point 0.5 G. So SA by G become as a 0.758. So now you can calculate the like you have the spectral acceleration as a 0.758 into G. So that is 7.436. So maximum lateral deformation is become as a D is equal to A by omega n square. So now the displacement is become as a 265.5 mm. Like if we double the section, like our deformation is also reduced around 60, around 40, 30, 40%. Okay, and our base shear is coming up to F is equal to KD. So that is 1400 into 0.265, 371.8 kilonewton. So that is your like the base shear that is increase, like that is increase in the system. Is there any doubt in the part B? Because that is the same as a part A, like only the stiffness is same. Any doubt?
No doubt, sir. No doubt from my side.
Okay. So now in the part C, in the part C, the stiffness is whatever the stiffness was in the part B, and the mass is considered as a now double. Now if the mass is doubled, then it what is my time period is become as the same. Whatever I get in the part A, like the because now the mass is double, so that will cancel out each other. So that will become as a 1.679 whatever than the part A. Natural frequency is 3.742. So from the response spectra, a time period 1.679. So it is give me to the SA by G is the same 1.072, and the design spectrum is zero point 0.5 G, and the SA by G is comes out to be 0.536. And if I uh, multiply it with the G, I got the 5.258, and the maximum lateral deformation is coming out to be D is equal to A by omega n square. So D is become as a 375.53, whatever we get in the first part. Now we will calculate the base here. It's coming out to F is equal to KD. So F is equal to 14,000 to 0.375. So that is the 525.7 kilometer. So that is the same whatever I get in the last part A. So this is a summary. Like in the part A, mass is given to you this 50,000 and the stiffness is this, and in this again in the second part the stiffness is double, and in the third part it is like both things are doubled. So my time period is like if the system is stiffer, then the time period is decreases. So displacement is like really reduces, but my base year is increases. Like if I increase the time period, like the stiffness, my displacement rather is decreases, but my base year is increases. So this is also a disadvantage for the system. So increasing the stiffness is also not a good option always. Comparing a part A and part B, so as the stiffness increasing, the natural period is decreasing, resulting deformation is also decreasing. But at the same time, the base shear is increasing. So this is a disadvantage. The part A and C, like in the part A and B, the system is doubled, like the natural period remains same, so the deformation is same. But at the same time, the base shear is also increases. So that means like over the response is coming out remain always in the system in the range of like the constant system. Like if we find out the velocity, like deformation, if you multiply with the omega n, whatever the omega n it is, for that velocity would remain same. So that response, all the response is in the velocity sensitive area. So if we want to reduce the deformation or we want to reduce the shear, we can go in the another like the reduce, like we can go in this area where the SA by G is lesser in this area, or like we can try another region where we can design our structures. Okay, so this is all from my side. Is there any question in the all the six questions, or are you facing any doubt in the assignment? Any doubt? Anything else? Anyone? Is there any doubt? Vasudev, do you have any doubt?
No, sir. No doubt for this discussion. Uh, but in earlier assignments, when one was the calculation required for omega d, that my value was something point 2525, something like that, or 0.2020, something like that,
Yes.
and that was related in between point 18 to point 2.
Okay.
So, sir, I will discuss it with in next lectures because I
Okay.
don't have my notebook at this time.
So that doubt is from whatever in the current assignment are you solving, or the doubt is from this the live
The
session
current
app?
current the current earlier assignment, sir.
In the which week assignment, week 4 or week 5?
Sir, I don't have my notebook right now. I will share it with in next lecture, sir.
Okay. Like if you like, do you have the solution of that assignment?
Yes, sir.
So is there is any difference in the answer you are saying, or something?
Yes, yes, sir. Yes, sir.
Okay, let me check if there is any
Yeah.
doubt.
Yes. Yes.
Okay.
Yes. Okay. Thank you, sir. Thank you very much.
Okay. Okay. Is there anyone have any doubt? Is there any doubt? Abhay Yadav, do you have any doubt?
No, sir.
Okay, so I am staying also here for the next 1 or 2 minutes. If anyone has any doubt, you can ask me, or else you can leave the session.
Thank you, sir.
Okay, sir. Okay.